Okay, in this problem, what we have is a molecule with two alkenes, so that's a diene. And we also have an alkene with an electron withdrawing group, that's a dienophile. And you're heating them together, so this reaction is a Diels-Alder reaction. In a Diels-Alder reaction, you react a diene and a dienophile to give a cyclohexene. And so if we number this, 1, 2, 3, 4, 5, 6, the double bond on the cyclohexane ends up between carbons 2 and 3. Now it's a matter of filling in everything. So in this case, what we'll do is go ahead and number 1, 2, 3, 4, 5, 6. 2 has an OMe group off of it. So put an OMe group off of 2, an OMe group off of 2. 4 has a deuterium off of it. Put a deuterium off of 4. 5 has an isopropyl group off of it, so I'm going to put an isopropyl group off of 5. 6 has a nitrile off of it. I'm going to put nitrile off of it, like so. Now, that's basically the rough outline. First thing to do, next thing we do actually, I should say, is check to make sure the strongest electron donating group on the dienophile, on the diene, the strongest electron donating group on the diene ends up either ortho or para to the electron withdrawing group on the dienophile. And what that means is ortho is when they have the 1-2 relationship. Para is when they have the 1-4 relationship. The third option is meta, and this is the option that you want to try to avoid, where they have the 1-3 relationship. And if we look in our diagram, the OMe, which is the donating group on the diene, and the nitrile, which is the withdrawing group on the dienophile, are meta to each other. So that doesn't obey the ortho-para rule, so what we have to do is switch 5 and 6. And have 5 and 6 be this way. Okay. Now, we got to figure out the stereochemistry. On the dienophile, the two groups are trans to each other. What that means is they're going to be trans to each other on the cyclohexene as well. And so, you pick a stereochemistry for like the electron withdrawing group. That's a wedge. For that isopropyl group to be still being trans, that must be a dash, like so. Next thing to do is called the endo-exo rule, endo-exo selectivity. The endo product is typically going to be the favored product. What the endo product has is the outside groups and this refers to the groups off of carbons 1 and 4. The outside groups end up on the same face as the electron withdrawing group, and the inside groups end up on the opposite face. And so we just have one group to worry about, and that's the deuterium. And if we were to label these alkenes as A and B, the deuterium is attached to alkene B. And we see it's a cis alkene. Alkene B is a cis alkene. So that deuterium is cis. And so therefore that deuterium is going inside the diene. And so that's an inside group. The inside group will be opposite the electron withdrawing group. So if the nitrile is a wedge, that means the deuterium must be a dash. And we're going from achiral to chiral, so you get a racemic mixture. Now it's just a matter of figuring out which one matches that. And that would be D. A, we can rule out because those two are cis. C, we can rule out because those two are cis. Then between B and D, D has the deuterium and the nitrile on opposite faces of each other. So this one right here is the exoproduct. That would be the product if the diene was this one.